All right, so last time we're talking about the Goodman. Criteria. We can make this go straight. Basically, the figure that if you add here the alternate stress, here the medium stress, okay, let's see. Yeah, let me show you. Might be a bit faster. I want to do this, but remember the medium stress was this one when is oscillating, no? Okay. So this is when the medium stress when you have a medium value. So let's say as a static load, and then the average is when it's oscillating. All right. So when we created the Goodman line, we said the first case was that okay, if we eliminate the alternating, this is going to break at a certain load that will be given by the ultimate or the yield value that would be either one of these 2 points. So for the Goodman line, we use the ultimate. We use this notation. And then the way it was constructed is that for the Goodman line, then if we eliminate the medium stress over here, the N, and we just work with the alternate, using the Palmer-Minor condition, this will be the number of stresses that you need in order for failure. You were able to create the line over this axis. All right. So for a Goodman line, we have the sigma E equal S sub E. This is just notation, so I'm not going to redo the figure again. But basically, we have this line for the Goodman line, for the Goodman failure criteria. And then we create another one that this time will be using the yield. And the yield value here. And this one was known as the modified Goodman line. So now we need to look at the criteria. All right, so again, this is kind of a review. So for Goodman line, I think that's what we stopped the other day discussing, is that if you are, so for a Goodman line, if you are above this line over here, that means the structure is going to fail. If you are below, that means that it's safe, no? Yeah, so this area here will be safe for the Goodman line. This is safe. Here will be not safe, okay, for the Goodman line. So the criteria for that one is that you have that the sigma alternate, which is the one on this axis, divided by the, I'm going to use the notation of the SE instead of the sigma because that's the one found more in the book. So SE equal to the endurance stress plus the mid-range stress divided by the ultimate, which is the Goodman line. Okay, we go from this point to this point. This should be equal to 1 over n, where in this case, n is the safety factor. So what's going to happen over here is that if n is higher or equal than 1, the structure will be considered as safe. If it is lower than 1, not safe. Okay, and we can do something similar for the modify Goodman line. And again, there's multiple lines. Okay, there's not only these two. If you go to a different if you go to a textbook, you might find 10 different versions for the fellow category. Okay, different lines over here. So with the sigma A over SY plus sigma M over SY equal to 1 over N. Okay, and over here, basically the same criteria for safe and unsafe. All right, so let's do one example. So let's see, the example is a 1045 hot rolled steel road undergoes a cyclic loading from a minimum stress value of 2 psi to sigma max equal 10 psi. The road has a hole in its center with what is KT? Look at it last time. What is it?
3.
What is it?
Oh, the value?
No, what is the meaning of KT? Is a stress concentration factor, no? Okay, so in this case, in the hole, it's said to augmentate the stresses by what? By 70%, basically, no? 1.7. I think it's supposed to be 3, no? For hole on the other ones, but in this case, this one, they say to use 1.7.
Oh.
So they say, let's see, the yield stress is SY equal to 45 psi, and the ultimate stress SU is 82 KSI. So here would be comma and the endurance stress is 20 KSI. Determine if the road design is safe or not. Okay, so here are the questions. So the yield value, we know what it is the one of the limit of the linear properties of the material, no? Okay, then we have the ultimate. So you see this one is 45. Does it make sense that the ultimate is much higher than the yield? This is that when you look here at the figure, if you look at the stress strain curve again, what do you have? You have so tropic material, okay, or for elastic material, you have this is, and this will be the SU, no? Okay, will be much higher. Now, does it make sense that the S endurance, oh, this should be S sub E, sorry, I put it U, I don't know what, S sub E. Does it make sense that the S endurance is much lower than the yield or the ultimate? Where is the endurance coming from? The endurance is coming from attaching the specimen to, let's say, to a shaker, and you move it this way, okay, until it falls, no? Yeah, from fatigue. So you see that from fatigue, when you have an object subjected to fatigue, the stress at which it's going to fail is much lower than the yield or the endurance. Yeah, that's important here to notice, okay? That's what I'm sorry. So when you do the design, and let's say you know you have a structure which is going to be subjected to some type of oscillating load, you need to be careful about which one you use, no? Okay? Or the data that you have available. So let's see what we have here. We know, so let's do first one thing. Let's do some figures. I always like to do figures. So we have a round over here. That let's say has a hole over here, which is going to imply that we have a concentration stress factor due to the hole of 1.7. Then what do we know? Is given to us over here that the minimum, okay, I'm just reading the problem. The minimum stress here, let's say, is, okay, I can do it here, doesn't matter. Let's say is equal to 2. And let's say the maximum is equal to 10. So I think last time I did give you some equations. All right, last time we derived, no, I give you this equation here for the mid-range stress and the alternate stress, no? Okay, so we're going to use these equations here. So we're going to have sigma sub m is equal to sigma max plus sigma min divided by 2, and the alternate will be sigma max minus sigma min divided by 2. So let's see, we do these values, what do we get? So we know sigma max is equals will be 10 plus 2 divided by 2, that should be what? 6. You see, in this class, it's not complicated math. There's no integrals, no? And then would be 10 minus 2 divided by 2. That will give us 4. Yeah, I was thinking about the results. Thank you. Divided by 2, 4. Okay, so what does that mean? The median is 6. So let's say, okay, obviously I'm not going to do it to scale at all. We could say here the median is 6. So what does that mean? Is that this is going to alternate between this value and this value here. Okay, this is moving this way. The magnitude, the alternated stress is just this one here, okay? Because you go from the 0, this doesn't mean that it's from top to top, because this just means that it's top, the load gets reversed, no? You want positive, negative, it's always the same amplitude. Okay, so that's basically what it means. So in other words, it doesn't matter if you bend something this way or this way, is going to be subjected to the same stress, no? Up and down. Okay, so basically now it's just a matter of substituting into the equation. All right. So next, let's see. We need to take into account what happened with this K sub T. So taking into consideration the stress concentration factor KT. We're going to call this one, let's say sigma bar sub m, which can you see or not? Because I don't see it. I think you can see. Will just be what? Will be K sub T times the sigma sub m, and the sigma bar alternate will just be the K sub T sigma alternate. So this basically just will give you what? So you do, I mean, let me write the first one would be 1.7 times 6. That would be what? 6 plus 4.2 now. So it should be what? 10.2 KSI. And the second one will be 1.7 times 4. That would be 4 plus 2.8. So it should be 6.8 KSI. Because I do 7 times 4 now, 24 would be 2.8. So let's say that we decide to use the, so let's say considering Goodman, Taylor criteria. And personally, I like to do figures, okay? If you ask me, I know this is the equation, but we're going to do it both ways, but let's do the figure. If we do the figure, what do we have? Over here, we have the alternate, remember? We're going to have here the mid-range. And for the Goodman line, what is the value? Go back to the line that is considered over here. What is the value? Is the which stress is considered there? Is the ultimate stress, no? So in this one, what is the ultimate equal to? Somebody mentioned saying 82, no? Okay. Now, for the alternates, what is the value considered? In this case, will be the, what is the one on the right? The endurance. So let's say the endurance will be here. Okay, I'll completely make it randomly. So will be here the endurance that we know is 20. So basically, the only thing you need to do is the line that connects those 2 points. Okay, so you see, you do the figure. This is the one I like to do it. Okay, then we do with the equation. Now, from this equation, what do we have for sigma sub n? That go on this one, which would be 10.2. So let's say, I know that will be 2 step, but let's say we'll be here. Sigma sub n equal to 10.2. And what should be the alternate? 6.8. So I mean, I know it's completely random, but what will be the point then that we are considering? That side, no? So let's say, let's call it point A if you want. What can we say at point A? We are in the safe area.
Whether we use S or sigma.
It doesn't matter. To me, it doesn't matter. What happened is that this is pretty old. I think on the old since you didn't have other different symbols when there were people writing books, then they're using the S.
Okay, thank you. Just want to make sure.
But you can use whatever you want. Okay. I think that's the reason. I'm not sure, but I think that's the reason. Because all this stuff is, and I've been using this for the last whatever. This is probably from the 30s, 40s, or 50s. Yeah. Yeah, I mean, nothing that we do is brand new, Okay. Right, and it works. Why are you going to change something, no? Okay, so now, if we use the equation, so let's say using the equation, what was the equation? We had sigma sub A over what? S endurance plus sigma sub M as ultimate needs to be equal to 1 over n. I think it's even harder to do this way because you need to do some basic algebra. So what should be the equation here? What is the one the alternate that we have? We have 6.8 divided by 20 plus 10.2 divided by 82. And this should be equal to 1 over n. So go ahead and solve, but I think if you solve the result, you should get 2.50. But go ahead and check if you want. But a bad thing to go and check. So if it is n much higher than 1, what does it mean is that it's safe, no? Like I said before, personally, I rather do the figure, no? You can compare, there is no algebra mistakes, no chance to do anything. Let's do exactly the same thing. Considering the modified Goodman Taylor criteria. So we can do exactly the same thing. Let's say we do the figure. So now for the modify, what is that we need? We need the, okay, I'm just looking here, we need the yield and the yield. So we go here from SE, let's say to SE. What is the value for SE in this problem? Did it give us the yield value? Yes, 45. 45. 45 equal to 45. So once again, what will be our point? Should be at sigma bar M, we say is 10.2, and the sigma bar is 6.8. So once again, what's happening to this point? This will be safe. Okay, and let's use the equation. I don't have the results here, but we can use the equation. Let me go to the next page. We do exactly the same thing as we did before. Using the equation, which is what for the modified Goodman line, we have sigma sub A over SE plus sigma sub M over SE needs to be equal to 1 over N. So this will give us what? 6.8 divided by 45 plus 10.2 divided by 45 equal 1 over N. Can somebody let me know what you get for N? 2.69, can you just put 2.7? Okay. But thank you for the calculation. So N much larger than 1. So this will be safe. Okay, so just one more thing, and I think Matthias was speaking, we're gonna be done. I mean, I could ask stuff, but I asked the other day the other instruction, they told me to stop over here. Which is good. That way we can go back and do problems and review everything until the final exam, no? Yeah, okay. Obviously, I will spice it up a little bit, no, on the way. Yeah. But we're never, what I want to say is that we're never going to go with new stuff. Okay. All right. So the other thing we're going to do now is just we talk about the endurance. Let's say this is just information. So estimation. Endurance stress. And number of cycles until failure. Okay, so again, here imagine that you have your, this is generally called, I don't know if that's the way they call it on your lab, a coupon for the material. You have generally you want 3, 4, no, this piece of material, and this one you're going to be applied on a shaker. So basically, you put it on the shaker, no? So it goes up and down if you want, up and down, no? Okay. So from here, you can have a curve which is S stress, S is stress, or we can put sigma. So this is called the S and curve, which is, somebody mentioned that then before, this is the fatigue curve. Okay, and if you look at this curve kind of curve is going to look something like this. Yeah, so what happened is that the lower is the stress value that you apply, the longer you're going to have the life, no? The higher the stress, the lower will be the number of cycles until failure. So basically, if I do a figure of what will be the loading due to this, again, you can apply it the medium or no medium. Let's put it that they say this. Nothing doesn't matter. This is just for information. This will be the loading, no? In function of time. So you want. So let's say at a point, let's say you get to this number of cycles. So let's say if you want your design to last, I'm going to completely make it up. Okay, let's say at this point n equal whatever, 1 million cycles. All right. So you can go here, you come to this point on the ascent curve, you go now to this side, and this point here will be 1. Your endurance stress, the max stress, if you want that, the maximum stress that for this number of cycles your structures can resist. Does that make sense? Yeah. Okay. Obviously, and the problem of this is that you need multiple lines, because what might happen now if somebody decides to do this? Yeah, if you want to do the figure, this is confusing. That's why I mentioned it. Here, let's say if you have a good thinking. So let's say now we move now, but instead of doing between the 0, we do it between a medium value here. So in this case, if this value is not too high, okay, look at this figure over here. Where do I have it? Things gone. So now imagine now, so this is about the 0 stress. Now let's say you put a certain amount of force initially on your coupon, no? Okay, and you do the same thing. Do you think if I need to put this curve, like a similar curve of this one, for this case, would it be on top or would it be on the bottom? This figure. So I mean, just make a guess, it's fine, you can make a guess. Should it be under or on top of this curve? What will be your guess? If it's under, that will be your guess, but I'm going to tell you it depends, because actually what happened to the stress, what happened to the structure if you increase a little bit the load? So if you say that the yield value is lower than the ultimate, it's because what happened as you start stretching a structure? What? Okay, with the phone call. Yes, so let's say you have, I'm talking about elastic material, okay, not brittle materials. All right? You agree that that's, well, probably you haven't done that stuff, but if you have a wire, which is made of such a material, and you tie it up, okay? Once you get to the yellow, you get to this point here, and then what happens? It becomes, without doing much effort, it's going to deform by itself. Okay, that will be. But then you're going to get to a view that actually the force created by the wire is much higher than what it was on the yield, you know, is what you see over here. Yes or no? Okay, so that's what is something, I mean, most of the time is that, let me give you an example, maybe a lot easier. What is, are you what is reinforced concrete? So yeah, concrete, you have bars of steel, no? You put concrete on there, you know. Okay, you put concrete on it. Oh, we can do that later on. It's good. We can do start reinforced concrete. It will give me an idea. But I put it this way. So you put concrete. You have the bars. Let's say you put the bars and you put concrete. Okay. Now maybe you have seen that or not. I'm not sure. But actually, to make it even stronger, sometimes what do they do to the bars? Before putting the concrete, they elongate the bars. Correct? What do they do that? The answer is here, because if you elongate the bar, now the resistance of the bar, the steel bar will not be the yield value. You can move it to what? You can move it to the ultimate. Do you understand what I'm saying here? So let's put it this way. Sometimes let's say you have one material. If you start pulling it at the beginning, it might be easy to pull it, but once you reach a certain force, it's going to become much harder to pull it. Yes? Yeah. So what they do when they do reinforced bars, sometimes if you stretch it, if you want, they stretch it up to the point that is easy. They stop it over here and then they pull the concrete. So that way it will be even more resistant. Okay, so let's say obviously that you do the design in this case. So I'm saying, if you do the design in this case, so you choose the right value, the medium value, then actually the curve sign for the stress for the fatigue line can be higher, no? Because you will be increasing the line. So it depends on how much force will you put. But obviously, generally, will try to do it so you move up, no? Do you understand? Yeah, I'm just doing this because of the concept. I want you to understand the concept. Does that make sense? You have any question? Okay, so that's why sometimes you want to pre-stress a structure. You want initially to have some stress so that you can move from the yield point from this area here to the ultimate area. No, okay, you're not going to move it to the ultimate, but you're probably going to move it to this area. No, that is still much higher. All right. Yeah, the concrete point is a good one. We can do that. So I forgot the number, the page numbers. We'll go back a little bit to what I was doing before. So I'm going to go to basic. Draft design, which we kind of did before, okay? Okay, so I don't have here the equation. Since you have all my notes, maybe you can go back. So shaft design is first, let's say part one. Design. Yeah, that's basically what I wanted. So basically, we say, remember that the final transmitted will be the torque times the angular velocity. And we know the equation of shear was for just the torque. So this is TR over J. Okay, and from here, I wrote the equation J over R equal to B omega tau. That was the basic, but then what do we say? We need to pay attention to what? Angle of twist. Why? Because if you have too much twist in the shaft, you have, if you have gears connected, you might have slippage of the gears, no, with each other. So you can have the design that will be safe for stressed, and this is what happens when you use tubes. If you use tubes, it might be safe for stresses, but tubes are gonna have what? They might have an angle of twist, no, too large. So you want to make sure that there's no much deformation, the angle of twist due to the force. You need to check it. And probably you need to either use a thicker wall or use a solid shaft. Okay, that will be your design. So you will be initial part. So then part two. We do that dynamic design, no? Okay, now you know that actually this is just for the basic, the amount of torque, the amount of stuff, this is pretty static, but now what happens is, you know, the shaft will be moving, so it will be a dynamic, it will be changing in function of time. So we're going to do the simplest case first, so case one, if you want. Which is just shaft in bending and torsion, which will be known as the fluctuating loads. This is basically connect to what we just did, okay? Is that the air condition?
There are no lamps above us.
Yeah, and what I was wondering as well. Okay, anyway. So basically, what do we say about the oscillating loads? We have done that many times already. Oscillating loads just basically means that okay, so we be the stress over here in function of time. And then let's do a figure here of a shaft. Doesn't matter, let's do this way. Okay, I mean, I just do figures, but it's not that. So what should be the shear distribution is something like this. You remember the maximum should be at the middle, no? Right here is just due to torque. So this will be due to torque. And now this should be due to bending, no? If you want. So bending and torsion. Okay, so this is the case of reverse bending, and because you will transfer all the time the same amount of power. Let's say you have a machine, an equipment that works at a constant RPM. No, the torque at a constant RPM will be basically almost constant. No, okay. So reverse bending, due to the motion, it will the structure will be bending up and down. And we can say nearly steady state, which means what? Constant shear stress due to torsion. So in other words, this figure here indicates the reverse bending, no, going from maximum value to minimum value. All right, and this will be basically almost constant. All right. Okay, so in here, I'm just going to do, in order to do the division for the explanation, I'm just going to say, let's just do another little figure here. Doesn't matter to write too much. So let's say this is our shaft, no? Over here, that is, let's say, rotating at a constant velocity, can be subjected to whatever different loads due to some type of support, whatever you want. Okay, let's say can be subjected to any type of load. Okay. And let's say we consider here one element, it doesn't matter. So over here, what did we say at the beginning of the shaft design is that you have a static section, a static part, and a dynamic part of the design. All right. So over here, for example, so following the same logic, we can say that the total bending stresses will be, we have a static component plus a dynamic component, which sometimes is called a dynamic fluctuating component, okay? Okay, so generally this is given as, you can rewrite this, let's say the total direct stress will be equal to the average of the static stress. The average will be, let's see what are the figures that we just did here. Will be the mid-range. That should be considered like the static one in some cases. Plus KT due to the dynamic. Here I'm just going to call it whatever, use the notation sigma sub R, and this should be S yield point divided by S endurance.
Is that what sigma R is? Is that yield or S endurance?
S is endurance, SY is S yield. This will be the stress of that element here.
Okay, so it's part of the equation.
Yeah, it's part of the equation. I mean, it's just to call this one here. Okay, and So if you want, this is bending stresses. So obviously we're gonna have the same thing for the shear stresses. Total shear stresses, we have a static component plus a dynamic or fluctuating component that will be tau will be equal to one here should be xy, but you can just put tau should be equal to the tau average plus a k sub t tau sub r sy over s endurance. Okay, so this is what the static component. This is the dynamic component. So in these equations, K sub T is the stress concentration factor, Sy is stress yield, and Se is the endurance stress.
How average be?
How is what?
What would how average be? Like sigma average and sigma n.
I mean, it will be the static load. So in most cases, that's what our average, but in most cases will be our mid-range. Yes. So for example, does that make sense? So when you do the mid-range, what did we do the other thing? So basically what we are here, what does that mean is that this structure will be oscillating here between this static value, no?
Okay, the min plus the mass divided.
Correct, that's what this is. That will be most in the case, but since this is more general, just put some type of average. But basically, this is the average. If you look at the definition, what is the median? Is the average, no? By definition. Okay. But if you want, since you have the question, if you want to come over here and say, if that helps you, let's say this will be the median for the alternate, and then we can see what that be. But what happens is that if you have an extra force applied over there, you see what I mean? Like let's say punctual load, then you need to add that one. Okay, but let's say in this case. In most cases will be the medium. So like I said before, this is something that I did mention, but we did not cover. But let's say most shots out of elastic materials. What time is it? Oh, sorry. Okay. Most shells are made out of elastic materials. For which the Mises stresses are generally considered. Okay, so for the von Mises, it means that you have square plus, this is, I don't do the derivation because it just takes too much time, but just take it over here. You take that is the bending stresses plus 3 times the shear stresses. For failure criteria, this should be lower than, let's say, the yield stresses divided by the N safety factor. What? Okay, so let's call maybe this equation here I, so Roman 1, Roman 2, and this big equation here A. What I'm going to do is to do what? I'm going to replace this sigma x over here. I'm going to put it over here. I'm going to replace the shear stress over here. I'm going to put it over here. Okay, that's what I'm going to do. So nobody else. So, oh, run out of paper. And I have a block. Here we go. So substituting. One and two into A. What do we have? So let's rewrite A. Okay, we have sigma x squared plus 3 tau xy squared should be lower than S yield over the safety factor square. We want to make sure we use lowercase m before, no? On the today. I think that's why I use lowercase.
Yeah, because capital M.
Okay.
Yeah.
Okay, letter n is safety factor, no? Okay. Let me just write it here in case. Okay, so I'll substitute the two equations are here. So for sigma x, I'm just going to replace, but I'm going to keep the average, okay? So this will give us what? So let's just write the first one. This will give us sigma average plus k sub t sigma sub r S yield over S endurance. Everything squared plus 3 times beta average plus k sub t tau sub r sy over S endurance. Everything squared needs to be lower or equal to S endurance of the safety factor square. Okay, so this is a general shaft design equation. Considering the von Mises Failure criteria. Okay, and if you want here, let me change something on the notation since we're gonna keep just like this one, okay? So the same thing here, this one will be most of the guy, in most cases, the medium. What do you think will be this one here? It should be the alternate, but in this case will not be alternate, no? In most cases. Okay, so for today, I'm gonna stop over here, but that doesn't mean we are done, okay? But we can talk about other stuff, about what we want to cover the rest of the semester. Let me stop the video. This is